Continue our discussion about the physics of the model, so we just rewrite the standard thing, so just for annotation. Okay, so this is the usual regression. Also, last time what we have seen is, we made an attempt of a model trying to predict, if you want, or to explain some of the hierarchy in this Java. Remember, we find it, we can always find the cases where this has this form. And remember that we introduced this U1 model giving charges to the different terminals here, all these indices, and we have seen that actually this model was successful to explain the hierarchy here in a, was a gradient between the hierarchy and the charges of the various fields under this U1 symmetry. And we've seen that okay, that was fine, but there was a problem with the Fibonacci general current, because then the natural suppression for the Fibonacci general current was not enough. Okay, so now so which was the let me recall the notation. So here we discussed already since the first lecture that we have is symmetry that is broken, okay, by the Java, but the standard model Lagrangian is invariant under this symmetry. And so the U1, the so-called Krogan-Dixon mechanism that I discussed at the time, that is a U1 subgroup, okay, it's a very little subgroup of this big group here. And that was, in a sense, not enough to protect the Fibonacci. It was okay to explain the hierarchy, but was not enough to explain correspondingly the suppression. Now we do really the opposite, and of course we don't have really a clear recipe, which is the
You can go ahead.
Sì, sì, è come se non esistesse.
Okay, so as we said the other time, we would like to explain two things. I mean, why these Y are so hierarchical, okay, and this is the sort of the standard model for the problem. And then at the same time, we would like to explain, to give a natural suppression of the Fibonacci general current with an effective scale not too far from the TV, okay, to accommodate new physics around the TV scale, which is consistent with the naturalness argument in the Higgs sector. Okay, so these are the two things that we would like to keep together. And there is no clear recipe. We don't know yet, actually, because we have not yet identified what's the standard model. So maybe one of the options that the effective scale of the standard model as effective theory is very high, so in that case we should not worry about this, but still trying to keep it a low scale. There are various options. So the U1 option doesn't work because of the reason I showed you before. Now we go to the totally opposite option, that is really trying to give this as a fundamental symmetry, or to some extent a fundamental symmetry, and so to consider the minimal breaking of this group, which is to assume that actually the Yukawa are the only breaking terms of this symmetry, also you understand. This is what goes under the name of minimal trigger violation ansatz. So how we can do that? So this is a bit different than the standard symmetry breaking that we have discussed so far, because the Yukawa are constant, okay? So we have to do a trick, okay? This trick is to treat the Yukawa as Furions. That is, we give some kind of fixtures, okay, transformation property to this object here as if they were some field, okay? And because of that, then in this way we can treat systematically the breaking of the symmetry induced by this guy. So let me be more specific. So you see here Why this one break the symmetry? Because okay, this is it's a 3-bar of, let me call it 3-bar to left. Okay, so it's a 3-bar of the symmetry of one of the 5 SU3 symmetry, which is this global SU3 acting on the Q left. While this term here, it's a 3 of right. So clearly, this object, if there are no other fields transforming under these two symmetry, this is not invariant. Then, if I say, well, let's give a transformation property to this object here such that this is formally invariant. So you say, suppose that this transform as a 3 times 3-bar, okay? Then of course, then clearly contracting 3-bar and 3 and 3-bar and 3, I can construct a singlet, okay? So I can deduce the transformation properties of the Yukawa such that this is formally invariant under the SU3 to the 5th group. In particular, in this case, it has to be invariant under these two SU3. In this case, it has to be invariant under the YD, the transformation property, transform as again, as a 3 to left, but as a 3-bar here, right, okay? So the idea is the following. There is some, the dynamical picture is the following. Maybe there is some dynamics, some very heavy speed, and we call it lambda f. Where the Yukawa, where some field, let me call them, some field, analog to the one that we introduced in the case of the UR, now a different field transforms. So here there is the exact SU3, and this field gets a value. And let me consider some dimensional combination. That I call Y, okay, if these are scalar fields, these are okay. So clearly, the idea is that this heavy scale, very heavy, nothing to do with this scale, the Yukawa are frozen to some value, okay? And the idea is that there are only these non-trivial values that they break the SU3 to the 5th symmetry. And then we have some implicit at the scale lambda from the order q b, okay? So if there is some dynamics here, this scale lambda, okay, that we don't know, maybe technicolor or supersymmetry, whatever. However, these dynamics, for instance, we know the coupling of q left I, q left j, q left k, q left M. Well, this dynamics has to respect the fundamental symmetry, but can violate it only because of the insertion of this term here. Exactly like you do for the say, the Higgs mechanism. So you break the symmetry via this. Yeah, which are not in that the Y. Okay. So then the effective operator that you will field are invariant operators in terms of this symmetry constructed in terms of the standard model field plus this Y treated as field. Okay. Of course, I'm cheating here because I refer to this is a systematic way to discuss, the breaking of symmetry induced by this object here. But I'm cheating because then these are not fundamental field, they are not dynamical field. Indeed, I will not discuss the dynamics here that is responsible for this structure. That's, if you want, it's a disadvantage of this approach. I cannot say what the Yukawa has to be, because if I want to say what the Yukawa has to be, I have to make some guess about the dynamics, and this is what I don't want to do. My only guess is, or my only assumption is that these are the only non-trivial object breaking the symmetry. And of course, there can be a lot of problems with the dynamics, since this is a scalar field, and this breaking mechanism is spontaneous symmetry breaking mechanism. There are some Gaussian boson here, so then I literally have to gauge the symmetry. But I don't care about it, because this is let's assume that everything happens at very high scales, okay? So that there are no light degrees of freedom surviving at energy, but the only effect surviving at energy is the fact that we feel the breaking of the symmetry because of this Y. Okay? So it's a technique, call it if you want, a Fourier technique, not to break the symmetry in the most general way, but to break it only according to certain breaking terms which have well-defined transformation properties. Okay. And let me just make since we were discussing qualitative analysis, maybe you see it also well see that there are no fundamental fields here. Okay. Suppose, for instance, that there is some new theory where there are some fields with the same transformation property of the standard model force. Okay. For instance, the quarks, the super simple. Okay. So the quarks are exactly the same type of transformation properties and the flavor symmetry of this guy here. And suppose that there is some complicated dynamics that break the flavor symmetry, and this dynamics, the fundamental flavor symmetry is not SU3 fifth, or maybe it's some U1 or whatever. Okay. Maybe something like what I discussed the other day. However, if I can build a theory where these are the only relevant operator at some time scale here, okay, then clearly all the rest is irrelevant by construction, okay? And so, if the dynamics is complicated, but it produces as only a relevant operator those associated with this field Y, okay, then the effect that I have a field at energy much lower scale is only the effect of this energy operator, okay? But here you see, it is exactly what could happen first also in the standard model. If in the standard model the scale of new physics is very heavy, then what survives at energy are only dimension for operator, which are this one here. So indeed, the U kappa in the standard model it's natural that we break the flavor symmetry only with the U kappa because there are no other operators in the standard model, okay, that bring the flavor symmetry. I have to put in dimension 6 operator to have something different. Okay. However, I want to have some dimension 6 operator close to the standard model scale to protect the Higgs master. Okay? So, I still want to insist that there is something at the scale that protects the Higgs magnetism, and then I know that if I put a generic new flavor structure at this scale, I'm lost because of KK mixing, mirror mixing, and so on. Okay? So this is why I have to make this answer that there are two scales. Okay? One scale where there is the flavor symmetry breaking, and the only relevant operator generated are some U kappa, exactly like this one, but maybe with other field, okay, some heavy field. And then they survive at low energy because these are the only relevant operator. Is it clear? This is a bit, well, it's a qualitative argument, but just to say that I want to build the theory where really the only breaking of this SU3 symmetry is triggered by this term here. Okay, so this is this idea. Okay, then now with the effective theory it's easy. Okay? Now forget about the dynamics, I don't know what happens, I just want to respect this idea. There is a fundamental SU3 to the, well, for the quark sector of course it's only an SU3 cube. If I have also directly connected to the field, and then this is broken only by the left, by the line. Okay? So, how can I build some operator beyond the standard model that respect these symmetry and symmetry breaking answers? So, for instance, let's start to consider a bilinear like this one. Right? Remember, the problem here, okay, I omit the Dirac structure because it's I can put it here just for. I want to take an operator like this one time, for instance, L bar. For instance, clearly, if I put an operator of the time, I, this is flavor invariant, so this is allowed. Okay? On the other hand, if I put I and J, is to break the symmetry, and so to pass from flavor to I need to insert some power of the U kappa field. Okay? Which power the U kappa field has to insert? Well, I need something that compensates to left. So, you remember now, so the transformation property are like this and like this. So I can insert both y up and y down. Let's start with y up. So if I insert y up, then this terms, when I contract the indices, compensate the charge of to left and then transform essentially as a U bar right, okay? But then if I put a U dagger, okay, I compensate this main transform as a U bar left, so this is invariant. Okay, so I guess it's clear, no? If not, just is it clear that this is so? This is a non-trivial flavor structure, okay, that we can build, and that respect these answers here. Now, what is? So let's consider the case where clearly you can go in the basis. So Q left is the usual data. So Q left is Q left.
Sorry, but we're the flavor basis?
We so far have not yet specified the basis. Okay, so this is I'm still in the, if you want, in the generic gauge invariant basis. Okay. Now, okay, I raised the structure of the Yukawa. I know that if I go in the basis where the down work are diagonal, so let me go in the down.
I'm just confused because we have Q left bar, Q left, which are supposed to transform in 3 bar, Q left, and 3 bar.
Sorry?
You have Q left bar and Q left before you insert the cows, right? And you just said they transform in 3 bar and the 3. So I don't see that you need to do this. That looks like
no, true. There is one flavor invariant operator which is this one. So I can this one plus.
Yeah.
Exactly. So I can write this operator. Okay, sum it.
Yeah.
Forget it. Of course, this operator is allowed, but this doesn't violate flavor. Okay, it's I.
Right.
So if I want to have something that connects I and j indices with I different from j, I need to put something. That's sorry. So usually I go too fast. So I want to build something that violates flavor. Okay, but it's so for instance, if you want to get connected to what we discussed in the case of the delta F2 operator, the delta F2 operator will be this one square. Okay, now contributing for instance to K-bar mixing or big bar mixing. So this is just an example, so it's not the only one, but it's an example of a non-trivial. Now, let me go to the down type basis. This is the case where you assume the form di dagger. Where this is the diagonal, while and okay. So in that basis, that is interesting to look at what happens when I look here to, of course here there is an up component and the down component. The up component with y up is always diagonal in the basis where the up are diagonal, because in the basis where the up is diagonal, y up is diagonal. So let's go on the other hand to look at what happens with the downward here in the basis where the downward are diagonal. So what I have is this down here. But I can put explicitly. So then this is the dagger lambda a square b. Okay. You see, okay, this is, I guess maybe you already see it, it's clear that this is exactly the same structure that we have in the standard model for the Fibonacci de la Casa, because this is, now we're talking somewhere else here. This is just the dagger, so on the v ij, and then square, okay? This is what this is, the diagonal matrix made in this form, okay, and up square and down square and top square, and there is a smaller square, okay, and then this is very small to a very good approximation. This is just in the limit where the top divided by the time square equals 2v, it's about 1, so this is roughly the diagonal 0, 0, 1. Okay. Or 0, 0, y top, to the top square. So this project here, in this approximation where I neglect this slack work masses, what I get here is VTI star, so it's the element W 3 I3, so it's TI star. Let me put it on the top square. On the top square, which now is just a constant. VTJ, okay. So that's exactly the same things we found when we did the computed the loop effect in the standard model. And it's not surprising because the standard model is by construction really not violated, because the standard model there is a proximity and the other proximity terms are this one. And actually the only big entry is the top of the count here. This is why I put here this term. For there is also a term of the type underneath. This is very small because it's proportional to the deep work mass, so it's much smaller than that. So this actually is the biggest term that one has for I equals to J. Okay. So yeah, it's then not surprisingly we get exactly the same type of suppression as we find in the standard model. So if I say now that there is an effective theory of this type, I put here a coupling 0 on the square, and then I can give the all other type of operator. So if I now, this is just an example, but if I build the tower of operator, I find exactly always the same thing. And the limit where I neglect all Yukawa coupling, I mean all the eigenvalue in the Yukawa coupling except the top one, this is the only relevant term, which is indeed the leading term in the standard model we compute for changing. Okay. And so then it's not a surprise that if I look at BBR mixing, I get exactly the same structure as in the standard model. So a generic amplitude of a Fourier changing, let's say, so Di equal to Dj, say plus whatever. So this could be BBR mixing, or just write it generically of this type. So it will be the standard model amplitude plus the implicit amplitude. Now the standard model amplitude we already seen what it is. Actually is some constant over the 1 divided by 16 pi square e square, and then there was this factor Vti Vtj, okay, y top square. We did this type of calculation, and what we find here is exactly the same thing, but now there will be some, for example, this is some c prime divided by lambda square, but then exactly the same secant combination. Okay, so I have v I Vj square. It's really exactly the same. So this is proportional. Okay, right. Put aside the secant factor to something that is the standard model coefficient divided by this scale that you remember we call it the lambda standard model plus the decoupling. Okay. And then the secant factor factorized. It's here. Alright, so it's clear that if we reach the level where we observe the standard model contribution, okay, the bound that we put here on the effective scale would be, okay, if we measure this with order 1 uncertainty, the bound when we put on the scale would be very similar to this effective scale here, which, remember, this is about 3 dB, right? And if we make a 10% measurement, we have to take the square root of 2, so it will be roughly a factor of 3 better than this, or they still be below 10 dB. Okay, so it will not be a huge scale because I naturally get a suppression of the transition because I put in this extra suppression factor. This is the point. So with this ansatz, which is clearly its ansatz, we enforce the same CKM suppression, okay, in the that we have in the standard model in the diffuse amplitude. Let me make a few comments. Is it clear here? So, I mean, one thing that maybe it's could be disturbing is the fact that these Yukawa coupling are a dimension, so they are not really, you cannot treat them as field, they are a dimension. So in principle, we don't have any extra suppression if we insert more and more power than you have capacity. So for instance, I could consider even at the level of dimension 4 operator, I could consider another operator of this type. Why you? For you. And so on. Okay. And so, well, first of all, in this case, this is exactly the same operator here. Actually, by definition, all the combination of operators that appear in dimension 4, they define the infinite count. Okay? So, at the level of dimension 4, we don't have to worry because there will be a sum of infinite terms, and all this sum is just of the type Q bar left, Q right, H times some 3-body matrix that I call the infinite count. However, for the higher dimension operator, then once I define the infinite count, the dimension 4 operator, the higher operator, I cannot define it anymore. So when I look to other operators, for instance, this one here, sorry if I'm stopped, so for instance, if I look to this operator here, this operator, now I have defined the infinite coupling from the dimension 4 here, I cannot redefine it anymore. So does this indicate a problem, the fact that I have several powers? Well, the answer is no, just because try to compute this, so this will be, I know what it is. This term, I know it from the masses, okay, and mixing at the free level. Then if I try to compute this term, this will be P dagger lambda u, okay, square V to the n, okay. But what it is, this is just, no, remember, so the structure of y u is just V dagger lambda u, so if I contract this n times, this is just V dagger lambda u to 2n V. Okay? So the secant matrix appear only once linearly. Okay? And actually, what I do, I even strengthen the hierarchy because I have more and more powers of here of this matrix, and this matrix is what here is bound. The yellow 0. 0 square. And so it basically again projects out only the component. And so this construction works in the standard model, not only because in the standard model there are only this operator here, but also because the Yukawa is so erratic. If here I couldn't neglect the potential masses, suppose that they're all of the same order, then I would get a big difference going from second power, third power, and so on. I would have a different type of combination. Well, on the other hand, the fact I have basically this projection to the third generation is what single out only one second combination. So it will be the peculiar structure of the Yukawa coupling. And unfortunately, in this idea, which is very powerful, but we don't have any explanation why we have this structure. So clearly, this we have to take it from combination. Okay, this is a bit disturbing. We would like to explain it. Okay.
But sorry, so we can consider more powers of the combination
yes.
Y dagger Y, and it's going to enhance the hierarchy, right? Because
it's going to enhance the hierarchy, yes, but basically it will not change the bound of the type. So if I consider this operator, okay, suppressed by 1 over lambda, I still find that it is consistent with the suppression scale of so in principle this operator is there. So I can put bound this operator on the other operator. Finally, will be a combination of this operator that is relevant, I can put the bound, and they all weight more or less the same, okay? Because they have, so, if you want, so if I compute them, maybe more explicit, so if I compute an amplitude, where there is this operator and the same operator, but now with n equal to 1, okay? So if I compute the amplitude here, I have that my amplitude is, and here I put 1 over lambda square, and I put the coupling, I think of this Cn, and here I put the coupling that I call C1. Okay. When I compute my amplitude, I get 1 over lambda square Cn, okay? And here I have y top square 2n, sorry, then I have my dt I dt j, okay, start, and here I will get c1 y top square dt I dj, okay? So again, this is, I can once more factorize this dkn combination. So I have Cn of the square y top square plus Cn 2n C1. So you see, just an effect, I can just, this is our order 1 number, so here I don't know which is the fundamental theory. Okay, this is what we call it some C tilde divided by lambda square, because these are both order 1 numbers. So the point is that, okay, I don't know which is the fundamental theory. Here I was only interested to see if I can put a stronger bound on this effective scale or not, and I find that no, because they are very compatible. Okay. So I don't find, in particular, I don't find any misalignment, so I don't find something which appear here with a different angle, okay, mixing angle between the family L and the family J, which would have been something that would destroy the agreement between data and standard model prediction. Okay. This is what this construction makes. Enforced a natural alignment in the SU3 space of Euclid's contribution versus standard model contribution. Indeed, just as a geometrical construction, I think I already mentioned this the first time. So, what happened here, if you think of the Yukawa coupling, so the Yukawa coupling are basically non-trivial direction in the SU3 to SU space. Okay? So we have this, in particular, let's consider the SU3 left space. Okay? In the SU3 left space, we have one. I plot it as a plane, of course it's not a plane, but just to give you an idea. So I have my y up, or better, what is really something that is really transforming only under SU3 is y up, that, okay? Which can be transformed only because in this way I contract the indices under right, okay, so this really transformed as a octet, so this is transformed as a 3 to left times the bar to left, which is either a singlet or it's either a singlet, and this would be the trace, or it is an octet under the symmetry. So this is a well-defined direction, and then there is the other direction, which is what it other. And what is the misalignment between these two guys is the Siegel matrix. Okay, so this part is not a plane, okay, but the Siegel matrix is the misalignment of the two non-trivial directions in the SU3 Fuller space. Okay, so if we assume that there are only these two non-trivial directions in the SU3 space, there is no way. All the amplitude will be always proportional to the Siegel matrix, okay, in a sense. Well, again, this example, illustrative pictorial example, was not really too serious because, again, as you see here, it's not really only the Siegel matrix, but the fact that the Siegel matrix plus the hierarchy that selects only the third component of the Siegel matrix. So it's the hierarchy plus the Siegel matrix that go together. So this misalignment, in a sense, contains both. Okay. So fine. So this is it's what is called this linear permutation. And of course, if you do it, you can try to build all the operators that you want, trying to respect this symmetry. You find that you will find deviation of the standard model that seems to be very small, okay, because it absorbs the standard simulation that you have in the standard model. Just to mention another example. So if I if I consider the operator di bar right, okay, now I think that this is the federal field. Di bar right, similar to Q left, and then this operator for to be invariant under the S2 needs to have a field, so okay, so this is the operator reference for P2S gamma. What I need to put here, well, what I need to put here is something that compensates the charge of the right, which is YV, but I put it darker because I put the bar right, okay? And then I have YU dark. So you can see that, for instance, if I want to do an operator that connects the right and to left, but in a non-trivial way, so not only via the Yukawa coupling, I have this type of combination. Okay, so for instance, this operator I can select the component contributing to B right S left, which is B2S gamma, and what I will have here is, again, working the basis where that work at diagonal, because these are my external field, I will have from here lambda b, and then I will have a usual combination d dagger lambda top square d elements 3 2, okay, so it will be b lambda top square b star b ts, which again was exactly what we found in the standard model by computing, well, sketching the computation of P2S gamma. So they are tend to be too sloppy. Okay. I'm sorry, you have to just make a mistake in the feedback with respect to the one. Yeah. Okay. Now, what I want to say? Okay, so this is that works. So, okay, you put here the scale you find here, the bound of the scale that you find here is at the level of FUTB. So the drawback of, I want to say, the drawback of this construction is very efficient, and actually, and it's called minimal field violation because you cannot have less than that. Okay, in the standard model, the symmetry is broken by the Yukawa. Okay, so even if there is nothing else that breaks the symmetry, so just take the standard model, for instance, and make consider supersymmetry. Okay, you will generate via radiative correction the breaking induced by the Yukawa. With the Yukawa, they are there already in the standard model. Okay, so it doesn't make sense to consider a model where there is zero flavor violation. Okay. At all. For instance, if I construct the square cross matrix, you have done the course of supersymmetry, so you know that I have what the scores are. Let me consider the MSSN where I have the scores. So, the generic mass matrix of the scores, let me consider the scores are blended. Okay? Let me consider now the LFN the scores, okay? LMS matrix, they are scalar field, okay? LMS matrix of this type. This one matrix could be, for instance, proportional to the identity at some scale, maybe at the gas scale, okay? This is an answer that you can make. Clearly, this is, in this way, I don't introduce new sources of velocity break. But now, use the scores, stick with the scores, because of the radiative correction, they will be connected to the force. They also have a Yukawa interaction. The Yukawa interaction is controlled by this coupling here. And so when you run out, for example, if you start with the Yukawa coupling, with the square constant that is one at some scale, maybe scale then when you run down to energy, this is a coupling constant that gets normalized. And what you will get is this coupling is normalized, so it will be a C C, okay, while I should equal times 0. So the mass, there will be a common renormalization, so it's like the renormalization of the mass in CD, but in Plato space this remains an empty matrix, but I will generate some correction of the type y dagger. Because this is allowed by the symmetry of the system. Okay? This model is another type of symmetry model, because it's a model where I still have the break of the symmetry induced by the standard model of coming. Okay? This is why, so finally, I generated this type, so if I build now effective operators that contains 4 fields and get out the course, I will generate contribution to the dimension 6 operator involving only standard model field that gets this type of insertion here. Okay. This is why it's minimal, because you cannot kill it. You can kill it maybe at one scale, but then on the scale it has to be there because it's allowed by the symmetry of the system. And also you see that this formulation is, in a sense, it's a renormalization group invariant. So I mean, you don't generate other things by the renormalization group if the only break terms are the Unicasper. You generate more and more power than the Unicasper, but the fundamental fields are on this one. Okay. Fine. Okay, so this is what is the minimal, is the most constrained structure, and one can do variation on the T, okay? As I said, the most minimal structure is the one with the U1.
One question now, the example of the dipole that you did, if you only insert one insertion of the YT, you get something a little bit super edge, no?
Instead of these two?
Yeah.
So of course, so there is that. So there is this one. But now if I go, so this operator is absolutely there. Now if I go to the mass state basis of downbox, it means the basis where YT is diagonal. Okay? So if I want to see the contribution to B R to S left, these do not contribute to BS because this becomes, okay, in the down adjusted basis becomes B right, lambda D I because it's diagonal, the left, okay? So the first one, again, the first one breaking, cutting flavor, cutting generation of different flavor is the one with the two insertion, right? I can do one with YD, okay, but that is suppressed. This way. So always the leading one involve Y, no way, in the standard model. Or in the standard model. So here we are in the standard model. In this minimal extension of the standard model, that means the assumption that we are breaking only very okay. But now I show you that even with very minimal assumption, we can get more structure. Okay, so this really you can keep it as a benchmark of the minimal things you can have. Okay, and sorry, I should have mentioned another thing. So which is the deviation of this construction? That it's testable. Okay, it's an effective theory that leads to testable prediction in flavor physics. Because now, suppose one day hopefully we find deviation from the standard model. So for instance, we measure better, improve the precision on the measurement of bitwise gamma. Okay. And we finally see from bitwise gamma and the standard model we can exactly compute the coefficient here. Okay? That is this one of the system by the factors. We compute it exactly. We measure, we also do the number to the correction, and we measure the 1 per mil and we find the difference. Okay? Now, this could well be accommodated by operator of this type, but also by other operators. Now, which is the prediction of the minimal flavor evolution construction? That since all the operators should satisfy this structure, so once you see a deviation in one process, for instance, you see a deviation in bitwise gamma, so let me be more precise. So, when you compute down the bitwise gamma, you expect in this construction some overall coefficient which is irrelevant, and then you expect D we have star, then you have the standard model, divided by 16. And then you have the new physics, divided by 1. So first, okay, we measure, we see that this step has to be different from 0. Now, if I look at another process, for instance, S going to be gamma, this construction predicts unambiguously that you have to have here S star with the S or the B star. And exactly the same structure. Okay, exactly. Because it's the same operator that contributes to B plus gamma to B to B S to the gamma. Even if I put here n power, it's exactly the same combination of n power that and n power that. Because, you see, I cannot treat differently the B with respect to the S. They always appear in this multiplet, okay, which contain the three family. So, the predictivity of this approach is that you predict that if you see deviation in a given type of transition, in the same type but changing flavor, you should see exactly the same type of deviation. So, it's falsifiable because if you see deviation and you don't see exactly this pattern, you have demonstrated not only that you have new physics, but also that you have a different breaking of the flavor symmetry in addition to the Pitagorian. So this is why it's usually useful. I mean, probably the most useful thing of this approach is that you build an effective theory and you cannot predict the size of deviation because we don't know what's this here. However, you predict a correlation. This is the power of effective theory is that of predicting correlation between different observers. So if you will see one deviation, then the specific symmetry breaking pattern tell you that you should see a deviation also in another observable. And if you don't see it, it means that you are breaking the initial assumption. So there are new sources of flavor symmetry breaking. Okay, this is very important. And also note that if I take the ratio, yeah, for instance, here new physics cancel. This is also interesting because actually the most precise test that we have so far involve ratios. If you remember, when I discussed briefly the measurement of the phase of people are mixing. But the basic we want is a ratio, because it's the ratio between the amplitude and this model. So, not surprising that, I mean, in this construction, all these ratios are automatically insensitive to new physics. So, it means that actually finding new physics is hard, because you really need to measure the full size of the amplitude to see the deviation in the model. Okay, but let's now look at the first simple variation on the theory, okay, which is the following one. Other questions? So the first simple variation is this one here. If you remember, again, the first lecture, I told you that, okay, there were these exutory to the fifth symmetry, but there were also some U1, remember, that we discussed. There were some, actually there are 5 U1s, and out of these 5 U1s, there is Bion number, vector number, which are not broken, but then there is higher charge, which also is gauged, but there are also 2 other U1. One, I call it PQ, and the other I call it, I forgot how I call it, U1 prime. These other 2 U1s have to be broken by the Yukawa in the minimal setup, like this. So let's consider in particular this one. Okay? This one, if you remember, corresponds to give a charge only to the down right and the right field. Sorry. This is a U1 charge, so the charge is the same for all the 3 generations inside. So this field has a charge. Now, there is no way to compensate this with the Higgs, because for instance, I could give a charge to the Higgs, but then I can compensate, but then in this case, I would break. You see? So, the only possibility is that if the Yukawas break the symmetry. Okay? The minimal approach, I treat it as a spurion that breaks also this U1 symmetry. Okay? However, if I now go to the next model, and it's a model with 2 Higgs doublets. So let me consider a model with 2 Higgs doublets. As I told you, clearly, if I put 2 Higgs doublets, I can, for instance, put a doublet that comes up, that has no charge, and a doublet coupled to down, that has a charge, and then this symmetry and compensate, so the Yukawa do not need to break the Yukawa. Okay? And you see these very simple answers, okay? Very minimal, well, it's not minimal because I'm really discussing, I'm extending the Higgs sector, I'm saying that there are two Higgses, but actually, and it's interesting because, for instance, you should have learned that in supersymmetry we have two Higgses, and actually they really respect this type of structure. We will see that there are very, very interesting phenomena. Still maintaining this Yukawa structure. And so let me start discussing a bit more general what happens with the model with two Higgs double. So, and sorry I will be sloppy, so I will try to save the things from the blackboard. And let me concentrate on the core sector, okay, because then for the rest of it's not too different. So what I have if I have two lists? Well, if I have two lists, in principle, before discussing anything about this Yukawa symmetry, I can have two types of interaction. Okay, I have the Higgs 1, okay, and the Higgs 2. So I define them such that they couple in this way to the downfield. So let me call this is the Yukawa 1, and this is the Yukawa down 2. But then clearly I also can write a Yukawa 2 to the field H2 C, or I could write to the field H1 C. No, so in general, that's the most general structure. In the standard model, we have only one, so we have only one, we have to do only one. Okay. So in the standard model, what I call H is this one. Okay. But if we have two, we have two. Now we see that this structure, clearly, if I allow it in general terms, so if I have two Higgs double, I have this structure, which are the physical degrees of freedom. So if I have two Higgs double, as you know, I have 3 bosons, which are hidden, but then I have 5 physical Higgses, which can be listed this way. So there is one that has the same quantum number of the standard Higgs, the boson, and then we have other 4 degrees of freedom, one heavy Higgs like the standard Higgs, one pseudo-scalar Higgs, and 2 charged Higgs. And okay, this I guess it's very simple, but just a way to figure out what happens. Suppose that one of the Higgs do not get a value. Okay, so then this will be the Higgs of the standard Higgs that get the value has its excitation, and then there is another multiplet which has 4 degrees of freedom, which is exactly this one. Okay. Okay, now if we have this structure, it's obvious that you cannot generalize at the same time the coupling, the master, because here the master, the effective master, for instance, of the up, let me call it this way, well, the valve combination is just, so what we usually call V square is just the sum of the two valves. This is just because of from the kinetic term of the Higgs, so yeah, in the Higgs sector again, H1 down H1 plus H2 down H2, okay? So clearly this both the covariant derivative, the masses to the double and the z, and the mass to the double and the z goes like v1 squared plus v2 squared. Okay, so this is why I call this combination the sum of two. And for convenience, let me introduce a parameter tangent beta, which is the ratio of the two waves. And let me do it in a convenient way. So let's assume that H1 has a big wave and H2 has a small wave. So this way, I call it V1 over V. So clearly, if you want the effective, if you want the yu of the standard model here, but this is the combination of these two. So the evolution model is V1 times V1 plus V2 divided by V. Okay. So this is similar for the data. So clearly, this is a specific combination that if I want to diagonalize the masses, I need to derive this combination, but then I will not diagonalize the coupling to this other field. So for instance, this is why historically it was thought a good idea to introduce the U1 symmetry independently of number violation, so just to forbid the 3 levels of children tracker. So if I introduce now a U1 symmetry under which only B right and B right are charged, so exactly the one I told you before, and then I say, well, only H2 is charged under this symmetry, then I can forbid this term, for instance, I can forbid this one and this one because this would violate this U1 symmetry. Okay? And this is indeed what happens in the most natural double model. This is why in such class of model this is usually called H up and this is called H down. And this is exactly the structure that you get in supersymmetry. So using that symmetry is a good way, independently of other aspects of Leo physics, to forbid 3 levels of trivial currents. Okay. Is it clear why we have 3 levels of trivial current if I don't put this extra symmetry? So you see, because I have, so the mass terms are controlled by this coupling, okay? So it's a specific combination of the two fields, okay, weighted by the power. So clearly when I diagonalize this term, I don't diagonalize the coupling to this neutral component, right? I don't do the exercise explicitly, but I guess it's clear. Okay, so let's enforce this symmetry. So if I enforce this symmetry, I can eliminate this term to 3 levels, okay, this will be this initial Lagrangian with this within the U1 symmetry. I told you I was wrong, so but now this symmetry, however, cannot be exact. And why cannot be exact? Because if it is, this symmetry then is spontaneously broken when this guy is rebel, okay? When H2 gets rebel, since H2 is charged, so this symmetry, this piece is locally charged, so that they are in line. But then this gets rebel, and so breaks the symmetry spontaneously. But then if the symmetry is broken spontaneously, I have a Gaussian boson. So actually, of the 5 field which I told you before, there is an extra Gaussian boson. One can show that the pseudoscala, if the symmetry is exact and only spontaneously broken, the pseudoscala is massless. So we have really a massless, and that is a true Gaussian boson, it's not gauged this symmetry. Okay? So since we don't want this extra Gaussian boson, typically, for instance, what one does is to break explicitly the symmetry in the Higgs sector, for instance, with the mass term, and this for H1. So if I put the count on the start, this is an explicit breaking of the symmetry, but now in the Higgs sector. Okay. Now, why all this is interesting? Well, the first interesting thing to solve, I think this symmetry, again, it's we can now proceed exactly like in the spirit of linear fluid violation, but treating also this U1 symmetry as a symmetry which is explicitly broken only by some term. Now, but the most interesting thing here is that then you have a coupling, okay, that you know what they are. In this case, you don't know what they are. Why? Because you don't know which is the relative weight of these two vectors. Okay. So in this simplified case, forget about the breaking of the U1 symmetry here. because the Yukawa coupling of the up, the one that I defined in the standard model, it's this one, but now I can erase the 1 and 2, is just this one times V1 divided by V. So if you want, in the standard model, the mass term was V times the Yukawa coupling. Here it's V1 by the Yukawa coupling. Okay? So the non-wave has to be equal to this one. Okay? So if you want, this is the way to express the standard model Yukawa coupling in terms of this x to the Yukawa coupling. And similarly for the down. Now, okay, I know what, so the standard model Yukawa coupling is, for instance, when I go to the eigenvalue, okay, the eigenvalue are what I call lambda u. The standard model are just the masses divided by this factor here, okay. So this is what I really know. I measured the mass, and also I measured the depth from the W and Z masses. So this is why I call it something that I know. But on the other hand, I don't know what this coupling is, okay, because I don't know what this bed here is. So let's consider a case which is interesting, phenomenology. That is the case where V1 is much larger than V2. So in first approximation, let's consider the case where V1 is much bigger than V2, and it will be clear now in a minute why this is the case. And so in this case, tangent beta it's very big, okay? And clearly in this case, B is about V1. So in this limit, this is about y. So if you want, y it's about the standard model constant. But in the case of y, what I have y d times v2 over v, which now it's about y d v2 over v1, which is what I call 1 tangent beta. And so what I find is that y d is tangent beta times the value of the standard model. Why is interesting in the case of large tangent beta? Well, because if you remember, in the standard model, the up Yukawa coupling contains the top Yukawa coupling, which is about 1. So for the third generation, at least we have one natural number, which is 1. Why the other two are suppressed? Maybe because there is some extra dynamic suppressed, but there is the third generation is 1. In this case, on the other hand, given the big work mass is small, so you see that if tangent beta is large, we have an explanation why the big work mass is small. But the big work mass is small is not because of the down Yukawa coupling is small, this is the third entries, but because the corresponding value is small. So here I put it the other way. So you see that the real coupling of the Lagrangian is much bigger than what we deduce from the mass. So this is tangent beta. Now the eigenvalue, the masses of the down. Okay. So if I put here the mass of the B, okay, if tangent beta is big, actually of the order of n top over n bottom, I can explain, I can also have the down Yukawa coupling as an entity over n1. Here, I presented in not the most straightforward way, but okay. The point is that one explanation why the deep work mass is much smaller than the up work mass is not because the Yukawa coupling is small, but because of the length is small. And what is surprising that we did, this illustrates the fact that we don't know what the Yukawa coupling are. Because the only thing we know well is the product of Yukawa times value. Okay? This is what we measure well from the masses. Okay? We don't know really the absolute normalization of the Yukawa. In a minimal extension, just to lift up, and this tangent beta has be 50. Okay? Actually, with the ratio 30, 40. And this is still in agreement with data, okay, without each product. And so how to distinguish between the minimal setup, okay, the case with 1 Higgs and the case with 2 Higgs. Of course, if you see 2 Higgses directly, if you don't see it, how can we distinguish with the flavor of setup? We can do it, and I'll show you why. So, let's keep that expression. So now, consider again the operator that I told you before. So we have that the bitwise gamma operator. Right. If I compute even just in the standard model with XW compute this correction, I find that here I should have this structure. I'm not convinced about this. Now, I will have Kaplan. And here, now here I should put the Higgs. Remember, because this is a SU2 charge, so I should put the Higgs. Which Higgs I should do? Which Higgs should I put here? X1 or X2?
H2.
X2. I should put X2, what? X2 tag, okay? Defined because of the charge, okay? Otherwise I will the charge. And you see that again, so when I mention bitwise gamma, what is relevant is the product of YD times the value of this guy here, which is again the equal mass. So again, I'm stuck, I cannot resolve. However, I told you, this V1 symmetry cannot be exact, because otherwise I would have pseudoscalar massless particle. So I know that the symmetry has to be broken in the Higgs sector. So in a model where the symmetry is broken in the Higgs sector, then I can also, and it will be broken exactly, I don't know, so there will be some other operator, and we call it define. And let me call epsilon, okay, if you want. The spurion breaking the U1 symmetry. So I can also write another. And so here I can do H1, right? Here this will be H. And you see, of course, so the fact that I put here, I violate the U1 symmetry, but maybe I didn't put this epsilon. So if the break of the U1 symmetry is small, okay, that's small. However, if the break of the U1 symmetry is not small, or if you want, supposedly, if the break of the symmetry, of course, only in the mass of the Higgses, okay, and there in the mass sector is big, it would appear here, for instance, via loop effect, okay? And so we'll get suppression because it's a loop suppression, but it's not more suppressive than this one, okay? This is, for instance, what happens, I'm doing this because it's exactly what happens in supersymmetry. Supersymmetry, in this term, is suppressed, but it's not more suppressive. So these are both loop type of suppression, okay? And now, however, I have a V1, okay, when I get the VEV, it not V2. So here, okay, so if here I have something which was MB times VTB star VTS y squared. Here I have the epsilon more, but I have V1, okay, and then I can express V1 in terms of V2 times V2, so I have NV times tangent beta, and I have the same pattern. So clearly, if tangent beta is big, in fact of 30, 40, this and epsilon is not too small, this will be a big effect. If epsilon is over than 1, which is realistic, this would be 30, 40 times bigger than this thing here. But you see, I have to go to the level of the higher dimensional operator to see this, the coupling between the Yukawa coupling and corresponding there. Okay? So to see really to see the fact that the cavitable is not the mass divided by the number left. Okay? And so this would be interesting. And you see that this type of effect, I see it only in this type of process where there are right-handed down forks, or eventually right-handed leptons. And since we discussed a few lectures ago about the G-2, the G-2, which has a structure in the right two-leg, is exactly one of the systems that could be possibly sensitive to an instant of the coupling in the left sector. So maybe not a surprise that we have seen some deviation in G-2, because that maybe the scale of the physicist, you see, I can push the scale of the physicist a bit higher, because then I can compensate with this coefficient which is big. So that's interesting. And so you see that it's not, and this is a model which is still minimal fluid coagulating in a sense that we break the esotrophic part of the flavor only by the Yukawa, okay? But with the part that we have extended the Higgs sector, we have decoupled on the breaking of the esotrophic from the breaking of the U1, and using this fact, we can get a big deviation from the standard model with specific range of parameters. So it's not true that in this minimum coagulating model you are always forced to have a small correction. You can have big suppression, big modification with respect to standard model in specific type, let's say this one, okay? But of course, this requires a bit less minimal construction. Okay? Okay, so the last, before we conclude, let me make a comment on the lepton sector, on the ferrocellulose in the lepton sector. So, what happens in the lepton sector? The cleaning is more tricky because let's look at the flavor breaking term in the lepton sector. So, remember we have that we have this coupling. And then we have seen that we need so this is I, J. And we've seen discussed that we need this master for the neutrino that we can write in this way. It's the first invariant operator. With this effective coupling Gij, so the mass of the neutrino is just Gij times v squared divided by lambda. This was the effective way to describe neutrino masses. And how can we deal with the flavor breaking? You see here is a bit clearly different with respect to the case of the quarks, because neutrino masses already appear in a irrelevant operator. Okay. This makes the situation a bit more complicated, less obvious. So in the case of the standard model, in the case of the quarks, was clear, it was a natural choice for the minima breaking terms which are the Yukawa. Because these are the terms associated to the only dimension 4 operator. Here, if you want the minima setup would mean no masses for the neutrinos. Just that. But we know that there are masses for the neutrinos. So we have to identify which are the breaking terms. And there is also this fact that we have the breaking of the total lepton number here, which also is different because of the board. So we have various options. It's not a standard reference framework. So let's list this option, at least the most obvious one. The first thing, suppose that this coupling Gij is the only coupling that breaks both the SU3 of the lepton, so I call it, maybe this is a bit, so this has nothing to do with the L, okay, of the big chunk, so this is just the SU3 of the flavor of the lepton, but also break the total lepton number, which I identify this way. Maybe I could call it this invent your commutation array. So this is just the SU3 associated with the flavor here. And then there's a U1, totally one charge on these two fields. So if GI is the only breaking of both these two, and then I insist on the fact that I want to have an effective scale close to the TV scale, that means that also this has to be close to the TV scale, then clearly means that this GIJ has to be extremely small, because I know from the neutrino mass, but the neutrino mass has and I know that these are the level of electron volts, so clearly if and this is big, so if lambda is only few TeV, then this coupling is extremely suppressed at the level of 10 to the minus 10, and so there is I will not observe any flavor violation, okay, whatsoever in process involving charge electron. Of course, I can do, if you want, a minimal flavor violating construction using this as the fundamental breaking terms of this guy here, and then I will not observe anything. So the typical operator that I can build is, for instance, is an operator of this type. I can write here, and then I have to put twice G, G, L, okay. So this is clear what this is. This is an operator that contribute, for instance, if I take here mu and I take here second generation, first generation, this is an operator that contributes to mu to gamma, here is water, and the coupling is controlled by this combination exactly like for the case of the upworking of coupling, but this is 10 to minus 10, 10 to minus 10, so it's really totally natural. So this, if you want, is indeed what you find in the standard model, so exactly using this Lagrangian, computing up to the 1 loop level, okay, putting that as the extra source of resolution break, you find no, okay, extremely suppressed effect. However, of course, there are possible variations, because I could consider that, as we already mentioned when discussing neutrino, that the breaking of the ferrous symmetry and the breaking of the U1 symmetry are controlled by different couplings. So, for instance, this scale here is very heavy because it's associated with the breaking of the total atom number, and then this Gij it's over the one and controlling the breaking of the SU3 symmetry. So in this case, I get exactly the same structure, okay? Exactly the same, but now this coupling are more than one. However, the point is that I don't know, well, I can, again, I don't know the overall scale of this coupling because I don't know this scale here. So you see, in a sense, it's a bit like the model of 2x's because I don't know the normalization, okay, of these breaking terms. So it's more difficult to control the strength of this transition in the electron sector. But if I construct ratios, okay, I can, for instance, if the ratio between mu to gamma and tau to mu gamma, this is controlled by this combination, and this is controlled by the neutrino masses, so it's related to the mixing angle in the neutrino sector. And since these mixing angles are big, I don't expect a big hierarchy between tau to mu gamma and mu to gamma. Okay. And so that synthesis, if you want, this is why in synthesis we try to search for tau to mu gamma, mu to gamma, because then looking at this ratio, I can see get more information about this count here. And finally, as a one B would be just to the count these two. But a more drastic option is to assume that G itself is not a fundamental coupling, but it's related to the contraction of some Vikawa coupling in the neutrino sector. That is, if you remember, is what we found when we introduced LFM neutrinos. So when we introduced LFM neutrinos, we find that okay, there were some fundamental coupling, which are pretend that you got coupling, and you find that then G is a perfect combination of these two without coupling, then you can build exactly the same. Then this becomes really analog to the quark sector, and then yes, you will not have that G, you will have something which is Y dagger, Y. In the other case, you get YE, which is then something different than the combination that you have in the neutrino masses. Okay. But in this case, you really have exactly the same combination of neutrino masses. So this combination is just M dagger M, that M is neutrino mass, but this is a different combination. So again, in the ideal case, where one day we will see mu gamma and tau gamma, looking at this, we can understand if the fundamental breaking comes from the U kappa or directly from or this is just the building breaking. And of course, all these options are open for me because we have not seen any of such transition. Okay, normally I think it's a bit early, but I think it's good to stop here before starting a different topic. So tomorrow we can discuss the third option, or the third type of option, which is connected to what Susan discussed about partial component dimension. But if you want, it's something in between. In the case of the U1 and the case of median collaboration, because it's the idea that again, these are not fundamental things, these are not fundamental breaking terms, but the fundamental hierarchy comes from the mixing between the standard of fermions and some eigenvalues median components.